Hi everyone, in this video we are going to cover the multiple choice question on the counting and relation. This is the second series of MCQs. Let's start with the first question. The first question we have in the POSET this, which pair of integer is comparable? Comparable means if either A is related to B or B is related to A with respect to the relation. So here we have the set of integer and this relation is a divide. We need to check as per these pairs which one is a comparable. Now whether 3 is related with 6 means whether 3 divides 6, yes. So it means option A is correct. So if we are getting any pair that is a part of a relation, then it means they are comparable. In this case, 5 doesn't divide 9, 9 doesn't divide 5, 5 doesn't divide 11 as well as 11 doesn't divide 5, 4 does not divide 14 as well as 14 does not divide 4. It means only option A is correct. Next question we have, which of the following statement is true? Greatest lower bound unique if exist, least upper bound is unique if exist, maximal elements are unique, or option A and B. You need to remember that least and the greatest word, whenever it is a part of anything, that is always a unique. या तो एलिमेंट हमेशा ग्रेटेस्ट होगा या सबसे छोटा होगा, तो वो हमेशा एक एलिमेंट ही होगा अगर उसमें है. So simply you can say that option A and B both are correct. Maximal elements are unique. It's not true because maximum elements can exist more than one. So it means option C is incorrect. So we can finally mark the option D. Next question we have, greatest element in a POSET is what? Now this is a set of positive integer and this is the divider relation. We need to identify the greatest element in a POSET. अब set क्या है? Set of integer with divider relation. So we need to find greatest element. If you construct its hash diagram, so starting with the first element, that is 1, 1 divides every integer, then we have 2, then 3, 4. So it means 1 is not correct, 2 is not correct, 3 is not correct, because for all 2 there exists an element that is greater than 2, that is 4, and for 3 we have a greatest element 6. If we have, this is a subset of this one, but there are many more elements above to this one, so it means D is the correct option. Next question we have, greatest lower bound of this set in this POSET is what? So now we need to construct the hash diagram in this case first, and the relation is again divider relation. So with the divider relation, take the first element. First element divides everyone? Yes. So we will place at the bottom. Now 2. 1 divides 2? Yes. So its level is 1 higher to the 1. Then 4. Whether 2 divides 4? Yes. So its level is 1 above to the 2. 5. Whether 4 divides 5? No. 2 divides 5? No. 1 divides 5? Yes. So its level will be above to this one. Next 10. Now 5 divides 10? Yes. Now whether 4 divides 10? No. 2 divides 10? Yes. So this is the final hash diagram we are getting in this case. We need to find the greatest lower bound of this set. Now first thing we need to think for the lower bound. So what is the lower bound for the 1? So 1 is only related with 1. So for the 1 we have only 1. For 2. So start from 2. Collect all the elements to reach at the bottom point. So that is 2 and 1. For 5 we have lower bound 5 and 1. For 4, collect all the elements that is in a path starts from 4 to bottom of the element. That is 4 to 1. For 10, elements are 10, 2, 1 and 10, 5, 1. So common elements are 10, 2, 5, 1. Now we need to take the lower bound of this entire set. not single elements. So we are considering the multiple elements. So what is the common element in all of these one? Common element is, that is 1. Now we have 1 only as the lower bound for this set. Now what is the greatest lower bound? Only single element is there and greatest is always unique. So we call 1 as the greatest lower bound of this set. Taking next example, which of the following pair of the elements are comparable in the POSET this? So again we have the set of positive integer with a divided relation. Comparable elements means either A is related with B or B is related with A. With respect to the relation means either A divides B or B divides A. We just need one pair. If that exists means elements are comparable. Whether 5 divides 15? Yes. So one pair is there. 5 divides 20? Yes. 3 divides 9? Yes. So it means all of these are comparable elements and hence we will mark the option D. Another question we have, if every pair of elements in a hash diagram has least upper bound and greatest lower bound, then which of the following option is correct? It becomes equivalence relation. No. Why not? Because hash diagram is only for the POSET. POSET means reflexive, antisymmetric and transitive. Whereas in equivalence relation, we have reflexive, transitive instead of antisymmetric, it is symmetric. So clearly A option is discarded. Option C says that it does not follow the reflexive relation. Again, it is completely incorrect because it is a POSET and POSET is always a reflexive relation. And basically, this is the definition of lattice. So if we take every pair of the element from the hash diagram and they have least upper bound as well as greatest lower bound, then we call that hash diagram as the lattice. Let's take one more example. Which of the following posets are lattice? So we need to identify which one is the lattice. So first thing, we will construct the hash diagram. In this case, we have the divider relation again. So whether 1 divides 2, yes, so its level is 1 above to this. Whether 2 divides 3, no. Whether 1 divides 3, yes. Whether 3 divides 4? No. Whether 2 divides 4? Yes. So level of 4 is 1 above to 2. Whether 4 divides 5? No. 2 divides 5? No. 3 divides 5? No. Whether 1 divides 5? Yes. So its level is 1 above to this one. Let's construct for the second case. Hash diagram for the second case is 1 divides every number, so place it at the bottom. 1 divides 2, so level of 2 is 1 above to this. Then 2 divides 4, yes, so its level is 1 above to this. 4 divides 8, yes, so its level is above to this. 8 divides 16, above to this. Now whenever we have such diagram, each and every element has a least upper bound and the greatest lower bound. Why? Because all of the pair are comparable. Note that in hash diagram, we never take a transitive edge. Like 2 divides 8, we never take 2 divides 8 by a transitive edge. We just need to figure out whether there is any way to reach at 8 from 2. Yes. If yes, then do not put any extra edge there. Now, each and every element are comparable, like 2 divides 8 as well as 4 divides 16. So obviously this is a lattice. It's very clear. Now in this case, it's very easy to discard this one as per this one. So whether 3 divides 5? No. Whether 5 divides 3? No. What is the upper bound of 3? Upper bound of 3 means we just need to collect all the elements that are upper to the 3. Only 3. For the 5, only 5. What is a common element? Nothing is there. It's like there exists no higher element for both the elements. It means it doesn't have a least upper bound, due to which it is not a lattice. We can discard the option A. Both A and B? No. Only B? Yes. So answer is C option. Next question we have, consider the divider relation M divides N on the set. The number of edges in a hash diagram is what? So let's construct that. So here first we will take the 2 element at the bottom. Now 2 divides 3? No. So it means the level of 2 and 3 is same. Now 2 divides 4? Yes. So its level is 1 above to 2. Whether 3 divides 4? No. So we will not join them. Take the next element 5. Any element divides 5? No. Even 5 doesn't divide any element in this case. So it means its level is at the bottom. Now 6. Which element divides 6? That is 2 and 3. So the level of 6 has one level above to these two one and we will join them. What about the 7? So 7 will be at the bottom because none of the element divides 7 as well as 7 doesn't divide any element in this case. 8. 4 divides 8 means the level of 8 is 1 above to 4. So here we have taken the 6 element. Whether 6 divides 8? No. Whether any other element divides 8? Yes, that is 2. But we will not join them because there is way to reach at 8 from 2. 9. Any element divides 9? Yes, that is 3. So the level of 9 is 1 above to the 3. Let's suppose we are placing here 10. Any element divides 10? Yes, that is 2 and 5. They both are at same level. So the level of 10 is 1 above to this. Join them. So this is the final hash diagram in this case. We need to count the number of edges. So the total number of edges in this case is first edge, second, third, fourth, fifth, sixth, seventh. So there are 7 edges in a hash diagram. Next question is number of edges in a hash diagram representing the partial ordering division on set this. That is this. Do not get confused that this is a symbol of less than equal to. No, we have already covered in the previous lecture videos. This symbol represents that it is a relation which is a POSET, means reflexive, transitive and antisymmetric. So there is a difference between this symbol and less than equal to. Now the relation says that A is related with B if A divides B. So we need to collect all those pairs and accordingly we need to draw the hash diagram. So without collecting the pairs, we will directly move to the hash diagram. Take the first element, put it at the bottom. Now 1 divides 2, yes, so its level is 1 above to this. 1 divides 3 but 2 doesn't divide 3. So level of 3 is parallel to the level of 2, 5. So again its level is parallel to the 2 and 3, 10. So level of the 10 will be higher to the level of 2 and 5. So let it 10 be here. So 2 divides 10 and 5 divides 10 but 3 doesn't divide 10. Next element is 15. Whether 10 divides 15? No. Whether 5 divides 15? Yes. So the level of 15 is one level above to this one. Whether 3 divides 15? Yes. 2 divides 15? No. Next 30. So 15 divides 30. So its level is 1 above to this. 10 divides 30. Yes. Now 2 divides 30. Yes. But we will not join them because there is a way to reach at 30. So here we need to count the number of edges in this case. So total number of edges in this case is what? First edge, second, third, fourth, fifth, sixth, seventh, eighth, ninth. So answer in this case is option C. Next question we have, for this POSET, what are the minimal elements? So here we have the set element and this is the divider relation. Again construct the hash diagram. So 3 is placed at the bottom, then 5 is placed at the bottom because neither 3 divides 5 nor 5 divides 3. What about the 9? Yes, 3 divides 9, so its level is 1 above to that. Whether 9 divides 15? No. 3 divides 15? Yes. So we will place that parallel to the 9 and join 5 and 15. Whether any element divides 24? Yes. Which one? That is 3. So the level of 24 is above to the 3. Now 45. Whether 24 divides 45? No. 9 divides 45? Yes. So the level of 45 is above to the level of 9. Whether 15 divides 45? Yes. Now 3 divides 45, 5 divides 45, but we will not join them because there is a way to reach at 45 from these two elements. Now we need to count the minimal elements. Minimal elements are always placed at the bottom. So here the minimal elements are 3 and 5. Hence option B is correct. Another question we have, for the partial order relation represented by this hash diagram, which of the following is not true? So here we have the least, maximal, minimal point. So let's identify what is the minimal element in this case. Minimal elements are always lies at the end. So A is called as the minimal. How many minimal elements in this case is? Only one, and this is called as a least as well. Now maximal elements, find the end point of each and every path. So we have this path, end point is E, here the end point is D, here the end point is F. So these all are called as the maximal element. Now point is, what is the greatest element? So when we have more than one maximal element, it means greatest element does not exist. Now identify which one is the correct option. So as per this, we need not a true statement. Whether D, E, F are maximal elements? Yes, but we need not. So we can discard this. Is D is the greatest element? No, because we are getting a more than one element as a maximal. So there exists no greatest element. That is the incorrect statement. Hence B is correct. Also check it, there is no greatest element as statement is correct. And there exists a least element. Yes, that is the A. Next question, in the following hash diagram, there are 2 least element, 3 greatest element, 3 maximal element, no minimal element. Clearly B option we can discard without looking into the hash diagram because greatest element is always unique. Now minimal elements are placed at the bottom, that is 2 minimal elements we have, and the least element is always unique. Here it is saying the 2 least element. Again we can directly discard this one. So no minimal element, discard this one. So option left as C, and that is the correct. Also check it, there are 3 maximal elements. End of the path is 12, 20 and 15, and these 3 are called as the maximal elements, and hence C is correct option. In this case, the maximal and the minimal elements of the POSET are what? So here the minimal element is 6. Not only 6 but 4 also, because here the path starts. So path starts either from the 4 or a 6 and they are placed at the bottom level. Or we can say that there exists no element that is lesser than the 4 as compared to the diagram. So 4 and 6 is minimal. Now maximal, so each path ends at the 1 or 2. So these are called as the maximal elements, and hence C option is correct. Taking the last question, what is the lower bound of this set? So how to calculate the lower bound of this set? So here we have the element A. So what are the lower bounds for the A? So we need to take a path that ends at the A from the bottom. Only there is a path that starts from the A as well as ends at A is this point. So lower bound is A. For C, so we need to take a path that ends at a C from the bottom. So from bottom to this. So we are getting 2 points. So lower bound in this case is A and C. For D, A, B, D. So there is a only way one to reach at D from the lower and collect all those elements, that is A, B and D. For the F, what are the ways to reach at F? So there are multiple ways. So either we can start from A to C, then C to E, E to F. Do not come back. So we just need to move in the upward direction. So we are getting the points A, C, E, F. Another way is A to B, B to E, E to F. So in this case, the unique element is B. Another way is A to B, B to D, and D to F. So unique point we are getting as a D. Basically, these are the lower bound of the A, C, D, F individually. But we need to collect for the full set. It means we need to take the intersection of all these. What is the intersection? That is A. And that is the final lower bound for this case.